Greetings Astronomy 10, and welcome back to Chapter 6, or... welcome back to Chapter 6, or the Inner Solar System, planets and moons and such. We're going to be talking about the Inner Solar System all week this week for 2 lectures. So you'll get Part 1 of Chapter 6 now, and our next class session will be Part 2 of Chapter 6, our second lecture. To begin with, I'd like you to look at the first image in today's image bank, and that is a table. I believe it's table 6.1. This is actually in your textbook near the beginning of the chapter. The first thing you'll note is the first 2 rows. The first one says semi-major axis, and the unit is AUs, or astronomical units, and that of course is the semi-major axis of Earth's orbit, right? This 150 million kilometer average distance that we are from the sun. And if you look in the Earth column, it says 1.0 because that is the definition of the unit, of course. And the second row, of course, is the orbital period in Earth years, not Mars years or, Moon years or Mercury years or whatever, okay? Earth years, okay? 365 and a quarter days in 10 minutes. Okay, if you recall from our physics lecture, Johannes Kepler contrived 3 major laws of planetary motion, and the third of those was a relationship in between the period and the semi-major axis of a planet's orbit. We said t squared, or the square of the orbital period, is equal to the semi-major axis, or average distance, cubed. And one would expect then, as the semi-major axis, or the distance from the sun, increases, therefore, too, also should the orbital period increase, but it should increase at an increased rate, right? Below 1, it should be even smaller. Above 1, it should be bigger. Cats. And that's exactly what we see. Cats. As we get further away from the sun, planets take longer to make their orbits. Also, if you recall, Kepler's second law of planetary motion, that is the so-called equal area, equal time law. And this law states that when a planet is closer to the Earth, it moves faster, right? And as a matter of fact, you can see in the third row, there are the orbital velocities of the planets. And Mercury, being the closest, of course, moves the fastest, right? As you would expect. Now, the mass of the inner planets don't really follow any kind of pattern. That's the next row down, and the unit is Earth masses. So when it has M for mass and the Earth symbol, the circle with the plus in it, that's Earth masses. And you can see that Mercury is about 5.5% of Earth's mass. Venus is about 81% Earth's mass, but Mars is only about 10% Earth's mass. They threw the moon in there just, because it's something that we're familiar with, and it's about 1% of Earth's mass, right? It's 6.24 times 10 to the 22 kilograms or something. Excuse me. But planets that are both closer and farther away from the sun, or farther away from the sun in comparison to the Earth, are both more massive and less massive. There's not like some kind of increasing scale like there is with the orbital distance and the orbital period. We can see that Mars and Mercury are very, very small by comparison, right? Mars being only about 10% of 1 Earth mass, and Mars being about 5% of 1 Earth mass. Not very big, not very massive. It is for this and some other reasons that we say that if there is a sister planet to Earth, it's got to be Venus, because Venus is much closer to our own mass. It's closer to us, right, in our solar system. It's got the closest orbit to us, and it's actually closer to us than any of the other planets. But Venus has a very, very strange orbit, and to try to put this into the proper context, what's the matter, Ninja? What's the matter? He's hiding in his castle. I don't know. Come here. Come on. Ninja meows. Oh, I got that ninja meows. So, where was I? Oh, right. If you look at the tilt of axis row, you'll see something really, really interesting about Venus's orbit. Now, to put this in proper context, Mercury has almost a zero axial tilt, right? It's 0 degrees inclined. It's basically straight up and down in comparison to the plane that it orbits around the sun, which is also synonymous with the sun's equator, right? And so Mercury has no seasons whatsoever, right? There isn't some time of the year where one hemisphere is pointed more towards the sun than the other or whatever. Not like we have here on Earth. The Earth's axis, so Mercury would be like straight up and down, and the Earth would be tilted at 23.5 degrees. And so part of the time, the northern hemisphere is going to be pointed towards the sun when we have summer, and then 6 months later, the southern hemisphere is going to be pointed towards the sun, right? When we in the northern hemisphere get less direct sunlight and therefore experience winter. But Venus is really weird, right? It's tilted like this, and so it actually spins backwards. And the weirdness, the strangeness of how Venus travels through space doesn't actually end there. Venus is kind of a really, really weird case. So it has an orbital period. If you look in the orbital period row in the Venus column, right, it says the orbital period is 0.615 years. That's 225 days. But the rotation period of Venus is 243 days. So it actually orbits faster than it rotates. Now, to put that into proper context, the moon has exactly the same orbital period as it does its rotation period, right? And so every time it revolves around the Earth, it also rotates once, right? And that's why the side of the moon that faces the Earth always faces the Earth. It is tidally locked. We always see the same side of the moon, right? And that's why we call the side that we can't see, even though it's not always dark, we call that the dark side of the moon, the opposite side from where we can see. Now, what this means, right, is if you were actually to rotate slower than that, slower than your rotation period, it would appear as though you're rotating backwards because you can't keep up with your orbital rotation, right? And so while Venus actually spins backwards because its axis is tilted all the way over, because its orbital period is shorter than its rotational period, it actually kind of appears like it's rotating forward really slowly. Although a day on Venus is kind of a goofy concept because it's, something like 200 some odd Earth days, right? The time that it takes for Venus either to rotate all the way around relative either to us or the sun is a really, really long time. Crazy stuff, right? In any case, Venus's mass, size, and surface gravity, because of the other two, are the closest to Earth's. And it's for those reasons that we say Venus is our sister planet. If you look at the surface gravity, Venus is about just shy of 9 meters per second squared, and we're short, just shy of 10. Usually we say it's 9.8, 9.81, 9.085. The book says 9.78 because they're taking like a global surface average instead of the sea level average, which is what we usually use in physics. But if Venus is our sister planet, she's like that mean stepsister or something, because the atmosphere of Venus is partly carbon dioxide, but also partially sulfuric acid. And it's for that reason that we've given up trying to get anywhere near Venus or colonize it, or, you know, we're looking at Mars instead. That and it's really, really hot on the surface of Venus, but that's another story altogether. Mars's surface gravity is about a third of ours. So you could imagine, you know, playing basketball or something on the surface of Mars, you can jump real high. And the moon, of course, is about a sixth of our gravity, and so that's even higher, right? You may have seen footage of astronauts jumping way, way up into, not the air, because there's no air on the moon, but jumping way, way up high, or playing golf and, you know, knocking the ball way, way far, that kind of thing. Yeah. And that actually makes, because the gravity on Mars is about a third of that on Earth, it actually makes trying to move like a rover or something like that across the surface of Mars sort of a complex engineering problem. The last thing that I want to point out from this table is if you look at the very, very bottom row, not the one that says escape velocity, the one below that, it's a series of images, right? And aside from the fact that only one of them is green, right, the Earth, what is different about the different images? There were a lot of them in the image of Mercury. There are some of them in the image of Mars. There's a lot of them on the image of the Moon. And there might be one or two small ones, but I'm not convinced that there are any in the image of Mars, really. Or, I'm sorry, Venus. I'm not convinced that there are really any in the image of Venus. And there are definitely not any in the image of Earth. And what is that? Well, if you said craters, then you would be absolutely correct. If we look at the number of craters on the surface of a planet, it kind of gives us a clue as to what's going on, obviously, on the surface of that planet, right? So why are there not tons of craters on the surface of the Earth? Spoiler alert, it's thought that there may be the same reason that there are no craters, there are not a lot, you know, on the surface of Venus as well. And that, of course, is volcanic activity or volcanism. So if there's a bunch of volcanic activity, right, you have lava coming up and plate tectonics moving and that kind of thing, and the surface is constantly overwriting itself. You know, every so many million years, the slate gets wiped clean, so to speak. And so having crater systems on the surface of a planet can really kind of give you a sense of the age of the surface, right? How old the surface covering is, how long it's been since there has been any volcanic activity. And if we think back to the picture that we have of solar system formation, how we got from a big cloud of gas and dust eventually to little particles of, you know, dust and tiny rocks to even bigger rocks to planetesimals and planets and so on. If we think back to the early solar system, there was definitely a time in our solar system's history, somewhere in this 5 billion year span leading up to now, that there were more of those tiny rocks and bigger rocks and bigger rocks floating around, right? And so, if there is a surface of a planet and there are a few craters in it, it's not that old. If there are no craters in it whatsoever, then it's really not old at all, right? Because volcanic activity is riding over it. Excuse me. If there are a number of craters, then it's probably older. And if there's like nested crater features, there's like a big old crater, and then there's craters in the middle of that, and there's craters in the middle of those, then you know you're looking at a really, really old, maybe billions of years old surface that has not been touched either by volcanic activity or other processes, you know, for a very, very long time. Because in the early solar system, there were more objects, right? More asteroids and things flying around, and so there were more impacts and therefore more craters. Now, we use statistical modeling and computer simulations and observations of how much mass there is in the solar system, things like that, in order to try to determine what the density of asteroids, what their average size was, things like that, at different periods in the solar system. Right before a bunch of the mass got swept up into the planets, there was a lot more of these asteroids and stuff floating around, right? And most of them, of course, in the disk, in what we call the accretion disk, around what has become the sun, right? Cats. Um, and so we can really kind of get a sense of how old a surface of a planet is if we compare the number and size of the crater features on the surface of that world, whatever it is, be it the moon or Mars and so on. Now, if that's true, we should be able to get some sort of clue as to the history of the Earth as well, right? We're also a member of this solar system. We were around when asteroids were bombarding planets, and small asteroids were becoming larger asteroids through collisions. Planetesimals were being formed, and so on. Right? We're still around today. That means we were around back then and a long time ago as well. Maybe not in the same large pieces, but we built up to it. It's and at some point we became mostly the planet that we are now. We've undergone some subtle changes and so on, of course. We know for sure that we have very few craters here on the surface of the Earth, and so we know that the surface of the Earth is quite young. But beyond that, we have to do what we did with our exploration of the history of the solar system in order to try to better determine what the planet is made out of, what the interior structure is like, right, and how we got here. And so if we try to build a model, there's actually there's a good image of this. This one's, I believe, from the United States Geologic Survey. It's the Earth on the left side of the image. You can very clearly see like the oceans, and there's like Scandinavia, and then Europe, and then Africa below it, right? That looks like a slice of that part of the world. And then there's like a cross section, and there's a bunch of what look like arcs, lines and stuff, curved lines. And we'll come back to what those are in just a second. But also, there's like a solid core, and then there's an area around it, right? And those are various layers of the planet. We're actually on the very, very top layer above the crust. Like there's the surface, where there's water and everything. And below that, there's this area called the lithosphere. It's like the crust in the very, very upper part of the mantle. And then there's this place called the mantle. And below that, there's a bunch of basically what we call magma, right? On the surface, it's called lava. Below the surface, it's called magma, right? It's just molten rocks and things like that. And according to our model of gravity and everything being hot and basically everything below the lithosphere being liquefied because of all the heat, what we would expect is that heavier, more massive elements, particles, would sort of gravitate towards the center over the course of time, and the lighter stuff would sort of float to the top. And water is not nearly as heavy as like iron and metals and things like that. And so we would kind of expect that all the heavy stuff would sink down and we end up with lighter stuff on the surface, and that's sort of indeed the picture, right? That much is pretty obvious because we're sitting on the surface of a planet that has lots and lots of water on it. Now, in order to test the theory that the planet Earth gets more and more dense as we go deeper down into it, we have to have some kind of clever way of trying to make that kind of measurement, right? Now, if you were a geologist or a geophysicist and you were trying to figure this problem out, what would you do? It's not an easy thing to try to discern, right? But fortunately, by this point in the semester, we have some understanding of waves, right? Waves, of course, are energy moving through various media, and in this case, the medium is going to be the Earth. And the waves that we're going to use in order to try to explore the interior structure of the Earth are seismic waves, the things that we usually call earthquakes, right? And essentially, what we wanted to do is to try to put a bunch of seismic monitoring stations all over the surface of the Earth so we can track the progress of seismic waves caused by events like earthquakes and aftershocks as they make their way through the Earth. And if we map out what we think it look like and when we should detect the wave at various points on the surface of the Earth, we can basically see whether or not we were right. Pretty clever, right? And so the United States Geologic Survey, in partnership with a bunch of scientific agencies all over the world, we set up a bunch of these little seismic monitoring stations all over the place to try to detect seismic waves. And what we found is that our predictions matched the model. We had to make some refinements and stuff, of course, but basically the idea is that the more dense a medium is, the faster sound moves through it, and that's why sound moves about 10 times as fast in water as it does in air. That's why whales can communicate over great long distances and stuff very, very quickly, right? Interesting stuff. And as I said, after we gathered all this data, we had to make a few refinements, but we were able to figure out not only how dense various parts of the Earth are, and especially right down to the core where it's the most dense, but whether or not it's liquid or solid and how big those regions are. And so we have a pretty good idea of what the interior of the Earth looks like, even though we've only drilled down like a few kilometers, you know, not super far. Obviously, seismic waves are just kinetic energy, right? The energy of motion, like a wave at the beach is kinetic energy moving through water. And these seismic waves will vibrate some matter, that vibrates the matter next to that, that vibrates the matter next to that, and so on. Kind of like how sound travels through air, right? And so tracking the progress of these waves has really helped us to try to figure out what the interior structure of the Earth is like. Most of the Earth, of course, is still molten or hot and melted, right? Liquid and rocks, owing to our active volcanism. Other planets most likely have more solid matter and less molten material available for volcanic activity. And there's a nice image of that as well that shows the various core sizes of the inner planets. And our data on the gravitational interactions, measurements for the planet's masses, and things like that support all of these models as well. I mean, obviously, we haven't gone to Venus and put up tons of seismic monitoring stations all over the Earth, but we think we have a pretty good handle on what the planets are like, what the inner planets are like, how they're structured, what their densities are, and so on. Now, the Moon possibly still has a molten core. It is tidally locked to the Earth as a result, and thus we only see one face of the Moon. And we were talking about that just a little while ago, a little earlier. But move this out of the way. But because of the moon's close proximity to the Earth, it has a very special kind of relationship to how things go here on the Earth, right? There we go. Now, the old theory about where the moon came from goes something like this. So here's the Earth, right? And there was an object the size of Mars that smashed into the Earth. And there was a big explosion, blah, 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 boom, right? And it knocked away a chunk of material, and that eventually became the moon. This, by the way, is the astrophysical symbol for the moon, right? It looks like a crescent moon. Now, the going theory behind why this is a good theory and why this has been kind of the leading theory for a very long time is that the Earth is still mostly bunches of magma, right? Hot molten metals and rocks and stuff like that. And so when this piece got away, by the way, this impactor, this Mars-sized impactor is called Theia. Whether or not it actually existed, we're not completely and totally certain, but for a long time it has been the most accepted theory. Now I'm going to draw it not to scale because I want the moon to be a little bit larger so you can see what's happening here. So doubtlessly, when this impactor smacked into the moon and knocked away a bunch of material, a lot of this molten material had to have been knocked up there into the moon as well, right? Now, because of the moon's close proximity to the Earth, it is thought that a bunch of this molten material, which is, heavy metals and dense rocks and stuff like that, was pulled closer to the Earth side of the moon, and then it dried and solidified. And the strong gravitational pull between the Earth and all of these heavy metals has kept this face of the moon tidally locked to the Earth. Unfortunately, according to the giant impact hypothesis, also sometimes called the Big Splash by astronomers, there is a problem. And that is that on the moon there are not a lot of what we call volatiles. And if you remember from our investigation or exploration of the origins of the solar system, volatiles are like chemicals that have a really, really low boiling point. And so they only condense out of a molecular cloud far away from a protostar as it's forming, right? Like out in the outer reaches of the solar system, we get more methane ice and things like that, because those are volatiles. Now, there are a number of volatiles here on the Earth, right? We didn't have any ammonia and methane and stuff like that in our atmosphere and on the planet and so on. We wouldn't have like ammonia cleaners that you use in your kitchen. But there aren't a lot of them on the moon. And this theory doesn't explain why very well. But a couple of years ago, it was UC Davis, and I think it was one of those Ivy League schools, Cornell, I think, came up with this crazy but interesting idea that actually, once you start to read up about it, it actually seems pretty plausible. So instead of there being a big object and a smaller one that smashes into it and knocks away a little piece, if instead it was two objects that were about the same size, and they smash into each other. No, that's my Ninja Meows. Go get your own whiteboard. Teach your own astronomy class, kitty. Okay, so they smash together here, right? And as these two objects of about equal mass smash together, essentially, they completely vaporize. Now, all of the material is not going to go up or down where all the mass came from, right? As these two things are smashing together, they're going to fly out kind of this way, right? And eventually they make like this toroidal shape, kind of like a donut, right? It'll make like kind of a spherical thing, and like it'll have like a spherical cross section here, but it'd be like a donut. This is like a donut cut in half. I'm sorry, my art skills are terrible, right? This is why I chose a life of science. But the going theory here is that while a bunch of this material, or all of this material basically got vaporized and turned into what we call a toroid, like a donut, right? It's got a hole in the middle, and it's like a ring, right? But the ring has got like a certain thickness, it's got like a sort of like a circular cross section. And all of the volatiles were suspended in this ring, right? All vaporized essentially, like the rest of the material. Now, if one of these original objects, right, had a certain amount of angular momentum relative to the other, like if they're rotating in opposite directions or something when they smashed into each other, it is thought that some of the matter could have started to swirl around, bits could have knocked into other bits, and eventually enough matter could have swept up together that it made a more massive chunk like the moon. And as it was being made, all of the volatiles were still suspended in this cloud, this thing we call a synestia. Now this kind of like explosion doesn't last long. This entire event from these things smashing together, making the cloud, and then eventually it all condenses back down and makes a planet. That, of course, was the Earth. That takes maybe a couple of days in total. And because of that really, really short time frame, and also the fact that it's really, really difficult for us to try to take direct images of planets in other solar systems, right? We've only taken, maybe a few dozen direct images. And for us to be lucky enough to see an event like this, that only lasts like 2 days, in the lifespan of a, 10 billion year old solar system or something like that, this may never actually be a testable theory. But it does explain why the moon doesn't have any volatiles in it. So maybe it's right. Who knows? Anyway, the moon, because of its close proximity to the Earth, has a very special relationship to how life on Earth goes, right? So I'm going to draw the Earth here, and I'll draw the moon here. Okay? Now, obviously, there's going to be a gravitational attraction, right? The Earth is going to be attracted towards the moon. But because of the moon's close proximity to the Earth, there will be a measurable difference in between the strength of the gravitational force on the near side compared to the far side. On the far side, obviously, it's farther away, so it's going to be less, right? In the middle, it's going to be somewhere in between. Obviously, at every point, there's going to be gravitational attraction towards the moon. Now, if we wanted to talk about the force that different parts of the Earth are going to feel relative to like the middle, right? That means we'll call the middle like 0. Right, and if the middle is 0, that means this is going to be less, and this is going to be more. And because there's less of a gravitational force on the far side than there is on the near side, the water and all like the loose particles, the atmosphere, make a tidal bulge. You probably heard about the tides, right? And the moon following the tides. Well, this is why. Because the gravitational influence of the moon on the Earth is less on the far side of the Earth and more on the near side. Simple stuff, right? And I know that I've drawn this tidal bulge to be basically facing the moon. It actually kind of lags behind because the Earth is rotating and, there's water tables and continents and all this kinds of stuff for the Earth to move, or for the water to move through. So it kind of lags behind, but that's, we'll talk about that maybe another time. Also, there is another tidal bulge from the sun, right? It's not as pronounced, it's not as big, because while the sun is much, much more massive, and its gravitational effect on the Earth in total is much greater, right? We move around the sun, not around the moon, right? The moon moves around us. But the moon is so much, or the sun is so much farther away than the moon is, that the difference in gravitational forces from the near side to the far side isn't as big. And so there's a second tidal bulge that follows the sun, and the larger one kind of follows the moon. Now it's possible that, let's say the sun is like here. What phase is this? This is the new moon, right? The side of the moon that's facing us is not lit up, right? The sunlight is going to light up this side here. And so this is a new moon. Now, during this phase, it is entirely possible that the sun's tidal bulge and the moon's tidal bulge align. And so we get a really, really high tide, right? This is called a spring tide. But it is also possible that the tidal bulge from the sun could be like at 90 degrees to the tidal bulge from the moon, right? And so that means all of the water on the surface of the Earth has to be divided in between the two tides. That makes both tides actually lower. This is called a neap tide. N-E-A-P. Like leap, but with an M. Interesting stuff, right? Long story short, the moon has a stronger tidal effect on the Earth than the sun does because of its proximity. But they both pull the tides, and they interact, because there's only a certain amount of water here on the surface of the Earth. Now, most of the Earth is molten, right? It's all magma and liquid metals and stuff like that, right? Right down to the core where it's all solid because of all the intense amount of gravitational pressure. Let me make sure I don't run over one of my cats with this chair here. So most of the Earth is actually molten below the crust, right, below the upper mantle. But here on the surface of the Earth, everything has sort of cooled off because above the surface there's the atmosphere, and above the atmosphere is space, right? And so all of the heat that we experience here can actually escape into space and into the universe at large. Long story short, the surface has kind of cooled in comparison to the rest of the interior of the Earth. Now, it may be tempting to think that the Earth actually stays warm because of the sun, and that is absolutely not the case. And as a matter of fact, if we want to talk about the total amount of heat that we experience, there is a temperature which we call absolute zero, which is at 0 on the Kelvin scale. This is the absolute temperature scale. That's equivalent to about minus 273.15 degrees C, or it's just under minus 460 degrees F, something like that. And then, all the way over here we have like 273.15 Kelvin, which is 0 degrees C, which is the freezing point of water, still really cold, right? And then here we've got like 25 degrees C, which is like, room temperature. Actually, I think room temperature is 20 degrees C. That's the standard definition, right? So this is like 293.15 Kelvin, blah, blah. This is like somewhere in the 70s in Fahrenheit, but we're not going to talk about. Actually, you know what? As a matter of fact, we're never talking about Fahrenheit again because Fahrenheit's dumb. Okay. the great lion's share of the heat that we experience on the surface of the Earth comes from radioactive heating, right? So this is radioactivity. That doesn't mean that you have to wear a hazmat suit everywhere you go or you're going to die of radiation poisoning. What that means is that most of the matter below the crust is stuff like, uranium and thorium, plutonium, lots of heavy metals and stuff, right? And as those decay into their daughter elements, they release a ton of heat, a tremendous amount of heat. And that is actually what keeps the Earth warm. It's about 90% of the heat that warms the Earth. Another maybe 10% or so is from tidal heating. And if you remember me saying that the tidal bulge that follows the moon actually lags behind it, it kind of lags by a lot. I think it's somewhere between 30 and 60 degrees. And the reason for that, of course, is that as the Earth rotates, all of that water, in order to try to follow the moon, has to go through water tables and continents and all this stuff, right? And so all of that water running into lots of solid land masses causes friction, and friction, of course, causes heat. And so we get about a tenth of the heat that we experience here on the surface of the Earth from tidal heating. And then the little bit that we get from the sun is like maybe, like a couple extra percent. That's like the icing on the cake. And so direct sunlight only gives us a tiny little bit. And of course that only happens during the day, right? Okay, that's it for today's lecture. I hope you have enjoyed today's lecture as much as I have giving today's lecture. If you have any questions, of course, please get a hold of me through the normal channels, and I will see you next time for part 2 of Chapter 6.